Okay, we need to start again. Just waiting for people coming back from lunch break. Okay, we can start in the meantime that the others will join. We just leave the open or the door open for a couple of minutes, then we will close it. So I hope you enjoyed the break, and we come back to the third section that actually will be the fourth session in the programs, because we have one of our experts that has to take the train to go back to the airport and take the flight to Switzerland. So we switch session 3 with session 4. So session 4 will be the next session. The section 4 is about building integrated photovoltaics. And the first speaker is Hassan Gholami from Multiconsult. I have to tell a story because I was your opponent for the PhD. Yeah. Honestly, I was really very enjoy reading your PhD. You have done a marvelous work, and I'm really happy that you are here today presenting. So Hassan holds a PhD in solar energy and BIPV from the University of Stavanger. He is now currently an advisor at the Solar and Smart Grid section and Multiconsult, and I'm very happy to hear is as an associate professor at the City and Regional Planning Group of the University of Stavanger. Hassan has developed skills and experience in techno-economic analysis and visibility study of solar energy system and BIPV, as well as energy system optimization. I'm really very glad you are here to present. The floor is yours, Hassan.
Thank you.
You want to use this one or the other?
I don't know which one is better. This one.
Yeah. Okay.
Yeah. Hi. Yeah. Good afternoon, everyone. I'm so pleased to be here to have this interesting topic with you, BIPV in urban areas. So let's just 15 minutes. Let's just quickly jump into the topic here. Should go to the next. Doesn't go. This one. How does it go to the next? This one. Yeah. Okay. Never mind. I can use this.
Now it works.
Okay.
Good.
Yeah, so just to make sure that we're on the same page, so just quick definition of the BIPV. So BIPV or building integrated photovoltaic are like PV system that like apply to the integrate to the building, and they perform they have two functions on the building scheme. So they are kind of power plants, so they produce power, and also they are building envelope materials. So to being building envelope material, they need to just have some specification that you see here, like mechanical rigidity, fire protection, and so on. And here we see some like different application of the BIPV on the building. So it can be discontinuous roof, yeah, and it can be rain screen, it can be integrated element, it can be curtain wall, it can be prefabricated system, also it can be like skylight. So different application for the BIPV system you can find on the building scheme. And then technologies, when it comes to the technologies, we have three main like viable technology for BIPV in the market now. And here we are going to like briefly see them and then see what is their efficiency right now in the market. So we have crystalline silicon, and their efficiency is something between 17, 18% to 21, 22%. And then we have CIGS, and their efficiency right now, the commercial version of the CIGS panel, the efficiency is like almost 20%. And we have CDTE or cadmium telluride, and the commercial version again of this CDTE is almost 17%. So they have their pro and cons. We don't go into that level, but yeah, we have these three main feasible or viable BIPV technology in the market now. And how we saw the commercial version, their efficiency, and how would it be in the future, in near future, in 5 years, in 10 years? So here we see a list of all the PV technology that we have, but just to see how would be those three technologies that we discussed. So the crystalline silicon, you see non-concentrator, the efficiency right now is the cell efficiency. And the research study, the cell efficiency right now is 26%. And for the CIGS, it's again 23, 24%. And for CDT, cadmium telluride is 22%. And normally it takes from 4 or 5 years to 7, 8 years so that we reach to this cell efficiency by panels. So those efficiency that we saw for the different BIPV technology, it takes less than 10 years to reach this level. So by 2030, maybe 2035, something like that, we could have CDT or CIGS by the efficiency of 22, 23%. So it's we cannot expect it huge jump on the BIPV efficiency for a short time. So that's for sure. And then when it comes to the color, we can BIPV, when it comes to the BIPV, we can have whatever color we would like to have. We can have whatever pattern we would like to have. It's just a matter of cost and efficiency. So here we see different colors from one manufacturer's side. So the best color, the best efficiency, and the best color that we could expect is dark blue and black colors. The efficiency, as we say, 20% or something like that. And when we go toward whitish, reddish color, the efficiency goes down to 10%, 11%. So with different colors, we can expect this range of 11, 12% to 20% for crystalline silicon. And as I said, you can also expect different patterns. Here we see this different beautiful patterns from Herman Technoglass with efficiency of 10 to 15%. And the manufacturer, for example, Camelon Solar. And they also just offer different pattern. Also, they have full library, 4,000 color. They can provide 4,000 color for the BIPV products with different efficiency, of course. In the cost components, so as I said, BIPV, so we have the BIPV has two functionality on the building. And when it comes to the cost component, of course, so we should relate or link this cost to this function. So if you say that, okay, at building envelope material, part of this cost of BIPV is related to that building envelope material route, and part of this cost is related to power plant route. And if you are going to do economic analysis, you never do this economic analysis for alternative material like glass, like wood, like stone, whatsoever. So if you are going to do economic analysis for BIPV system, this is the cost that you should consider at the initial investment. And what is this initial investment? Just quickly, the system cost for BIPV roofing, you see it's just ranged from 200 euros to 400 or 500 euros, while the traditional material, they cost from 100 to 200. And when it comes to the BIPV facade, the regular facade or traditional facade element, the cost is something from 200 to 400. And the BIPV facade, their cost is from 400 to 800. So if you are going to, for example, again, if you are going to do the economic analysis for a facade, BIPV, installing the facade, what should you consider the cost difference between this and this? And that's just changed a lot, this economic analysis. And just quickly, this is one of our study that I did during my PhD. So what is the potential of the BIPV in Europe? Here, for example, we see, for example, in Oslo, the average production of the BIPV system for different facade is the roof. Here you see that again the south facade and roof, the production per square meter is so close, and then you can expect 60% of the south facade for the east and west, and for the north facade, of course, you can expect just what you expect is so low, 40 kilowatt hour per square meter. And the same, as you see, what is interesting here, just quickly, you see that the production, for example, for Norway in Oslo is so close to the production in Germany in Berlin. If I remember correctly, yeah, at least for the facade, for south facade. And we see there is a lot of subsidy and promotion plans for like Germany in Berlin, but hope we see something similar to that in Norway. It will change a lot the market. And so we have that huge potential. So what is the levelized cost of electricity for this BIPV system, which is like unit cost of production over the entire lifetime of the BIPV system? So we did like another study. So we considered two scenarios, one for considering the total investment, initial investment for the entire cost. And in scenario two, we just consider the cost related to the power plant rule. And as we see here, just to discuss EU in average. So when we consider the total investment, the levelized cost of electricity is less than the network price, which is network price is defined here like the cost of the electricity cost of the end user. It is spot price plus the cost of the grid plus tax and so on. So the levelized cost of electricity is less than network price, even considering the total investment. And if you consider just the cost related to the power plant rule, you see the LCO would be almost half of the network price. So it means that, okay, it's going to be very profitable. It will be a good payback time and and IRR. And so we saw the economy, we saw the potential. So how does this BIPV can contribute to the nearly zero energy city? We did another study to see the relation between the building skin and also building net area. So just quickly, building net area is the gross floor area. BS is building skin, and this BSGR building skin glazing ratio. So 50% BSGR means that 50% of the building skin is covered by glass or glazing solution. So just again, for EU in average, for example, 0.88 means that by the study that we did show that the annual electricity consumption of 1 square meter of the building net area can be supplied by 0.88 square meter of the building skin. So this is a good like indication or indicator or matrix for like urban planners to see how they can just link this building skin into the building net area and exactly the right to light and so on to just link this together. So even if they don't consider like solar solution for the facade, at least keep this like this ratio as low as possible for the future generation, for the future like renovation, so that when this building is going to be renovated in 50 years or 60 years, there will be huge potential for solar application on the building. And the next topic is the like energy input for PV production. So for most of we have several projects where the architects in that project are so concerned about the energy footprint or carbon footprint of this BIPV solution that we offer to them. Just a quick discussion here. So when it comes to the energy input for PV production, the energy input, for example, for monocrystalline silicon, we see here for made in US or made in EU, made in China. We see the energy footprint is almost the same. But when it comes to and also it changed by the technology, not by the country, the energy footprint. But when it comes to the carbon footprint, which is important for architect normally, it varies a lot by the country of origin as well. So it's like sensible to the country of origin and also technology, which is matters a lot. So for example, made in EU monocrystalline silicon, carbon footprint is almost half of the made in China monocrystalline silicon. And if you change the technology, you see, if you change the technology to CDT or CIGS, it will be way less, even way less. And a quick slide about life cycle energy footprint. Here again, we have another slide that shows, okay, if we consider for crystalline silicon, we can expect like 1,300 kilowatt hour per square meter to like install a PV system, and then you can expect like 8,500 kilowatt hour per square meter. Electricity in a lifetime. This is for Denmark. And if you do a proper end-of-life material recovery, you can expect almost like 80 to 90% of the electricity that you use to install the system. This shows how you can just the life cycle energy analysis of the PV system is. And this is for crystalline silicon and chain bonding technology, of course. And the impact of orientations. So here we see just the production over a day, over months of a year, and also over the years. So as we see, of course, we can expect like good production for the east method during the morning, west method during the evening, and also roof and south method during noon. But the thing is that if you mix these different orientations, you can have a great distributed electricity during the year, during the day. We will see later. And also, when it comes to different monsters, here we see that you can, by like having roof-mounted or south-mounted PV system, you can expect a really good production in May and July. But if you use south method, you see you're going to have really good production during different months of the year, from March to October, November. Sometimes it's like better solution for like some demands. It depends on the demands. For example, if you have a lot of cooling demand, then like roof and south might make sense. But if you have like distributed demand over a year, then facade might make more sense. And here again, this is another example of how by like mixing different orientations, you see, for example, east and west, you can just have different production profile and match it to your demand profile. And finally, the challenges in Norway, just quickly. So we did a like markets report study for solar energy cluster in Norway, solar energy Klingen, which is available. You can read it here in Norwegian. But yeah, the main challenges in Norway is lack of experts both in design and installation. So in design, it means that as a like solar designer in a neighborhood, you need to be able to discuss this BIPV or solar project with electrical engineer. When you talk with electrical engineer, you need to talk about specific production, watt peak, and efficiency, maximum exported power to the grid, and you need to talk with mechanical engineers about the like load bearing capacity, rigidity, and then you need to talk with fire expert about the different fire category. You need to talk with architects about the aesthetic aspect, production per square meter, green certification, and so on. So you need to talk with different disciplines, with different language, and you need to be able to translate all this language together. Sometimes it becomes a bit challenging. And regulatory hindrance, we discussed it before in one of these presentations. Yeah, we have a lot of experiencing a lot of challenges with regulatory hindrance, but still a lot in Norway. Yeah, new regulation hopefully will be implemented soon that will like remove will lift a lot of these hindrances. And the misconception of high initial cost compared to alternative, as I said, yeah, it's really important to see what cost, what is the cost that you consider the initial investment. And yeah, that's it, I think. Thank you. Yeah.
Thanks a lot. Thanks a lot. Thanks a lot, Hassan. We will have a question afterwards for you. We go ahead with the second speaker of this session, which is Gilles Destiaux. Gilles is an associate professor at Genève Institute of Landscape Engineering and Architecture, APR, which is also partner in Elias. And he is a senior consultant in urban energy planning in the company Amstein and Waltert in Genève. I think it's enough. You have too many specializations, so I think it's better that I stop here.
Thank you. The microphone is okay.
The microphone is okay? No? Okay.
Okay.
Can you use this one?
Yes, yes,
Yeah.
yes.
In the meantime, I put your presentation.
So, like this. Thank you. So, good afternoon. My presentation is about assessing solar potential on the facade at large scale in urban areas, and particularly focusing on the reflection components in urban canyons. And I will also show some example in a Geneva context. So I'm working on solar modeling urban environment, particularly contributing to the task 63 through 3 projects. So the project of the solar cadastre of the Greater Geneva, Helios, both were introduced today, and the Valles project that I will present now about solar facades in urban area. So solar, as it was very well introduced in the previous presentation, solar energy on facade is gaining more and more importance due to, in particular, to improvement in architectural and integration and democratization also of color modules, as we've seen. It is particularly relevant also for Nordic countries when the sun's position is low, and also in more Central Europe in winter, where the sun position is also low during the winter. So the main limitation concerns the lower efficiency comparing to panels used on roofs, as we've seen also, and of course the cost and the complexity for existing buildings with a solar panel installation on facades. But globally, it is really worth gaining importance in that. We've been working on solar facades at urban scale for a couple of years through different projects. We have the references here, but so far we haven't used appropriate strategy for modeling solar reflection. And we also have been basing on poor level of detail without taking into account the texture, facade texture like windows. So those gaps motivated us to initiate this project Valles, supported by my university and also the energy service company of Geneva. So we wanted to reach 2 main goals: to model the texture of facade with focus on windows detection, and to model the reflected component of solar radiation with an appropriate or adapted strategy for processing large urban canyon, that's a large urban scale canyon, and also with a reasonable computation times. That's the most important thing. So about the first objective, about facade texturation, we used a photogrammetry approach. So the aim is to build a digital twin of an urban environment, which consists in texturing 3D building models. So we have already some texture match, but not georeferences. So the idea is to bring all together, and we were based on oblique also photos that were processed with photogrammetry. And from that, using machine learning techniques, we can automatically or semi-automatically detect windows with a given interval of confidence, as you can see on the image. For reminding, solar radiation has 3 components: so the diffuse, beam or direct, and the reflected components. And I will focus on this component now. In previous work, we were able to compute let's say, the primary radiation, which is the direct plus the diffuse radiation on large urban scale. And here we would like to process reflection from this primary irradiation. So we, as you can see, use different inputs data, cadastral data, digital surface model, and then we can process shadow casting in urban scene. And then the new component is the rates about reflected. So for processing reflected radiation, basically there are 2 main approaches. So the first approach is the specular one, based on ray tracing method. And the second is the radiosity, which is a more uniform method, and it is more adapted also for processing large urban scale. So this is an iterative process. The global radiation is the sum of the source, which is in the first iteration the primary irradiation, and the reflected component is expressed by the albedo, the reflection coefficient. The global, which is in the first iteration the primary radiation, and the form factor, which is the most important component of processing reflected radiation. So let's consider that the urban scene is modeled through a set of meshes. The form factors consist in determining the intervisibility between meshes. So how one mesh sees another mesh or doesn't see it. So if there's any obstacle that will interrupt the intervisibility. So this is this kind of formula of reciprocity between the two mesh. But you can imagine that using this approach, so processing intervisibility for each pair of mesh is very demanding in terms of storage and computation time. For instance, for this scene of 300 meters of 140,000 points, the intervisibility, the form factor matrix will have billions of occurrences to consider the pairwise of intervisibility, which is a very high amount of storage, and it will also require, so we don't see the slide, but it doesn't matter, just it would also require 1 week of continuous computing. So it is too much for a rather small urban scene. That's why we introduced in this project a simplified approach. So instead of considering intervisibility between each pair of mesh, first of all, we model mesh as a cloud of points, which is more simple. And we project for each scene point a virtual hemisphere or sphere. And then we consider not the ray between each scene point, but between the scene point and a sphere or a sky point or sky mesh, if you want. So and so we consider if there will be any obstacle that will cause some reflection on the scene. So it means that instead of having billions of points, we have only some millions of points. That will reduce dramatically the storage and also the computation time. So we decrease from 1 week to 1 or 2 hours of computation time using this scene, and also using just a prototype of code which is encoded into MATLAB, which is not so efficient, but anyway, you can see the difference. So if you want to know more about this, here's a recent paper that we published that explains all of that. So let me now present you an application of these modeling tools. It is a residential neighborhood area in Geneva, close to the famous research center of CERN. So let's consider this building. You have here a blind wall, and also here the longest facade with the mix between opaque elements and windows. So the idea is to promote solar facade for in the perspective of renovation of this building. So here's the way it works, considering all the process as I introduced previously. So first of all, we have to analyze the albedo for each scene point on the ground, facade, and a roof. So we have Geneva, some GIS information like a ground coverage layer. we calculate the form factors. And then, so in the second step, we calculate the primary radiation, direct plus diffuse, the reflected radiation in 2 iterations, 2 orders, that combine form factor, albedo plus the primary radiation. And then we have here the global results, global radiation. So just remind those 2 points. We will compare that after the result between a roof and south-oriented surface. So we have processed all the scene, but just consider the result on this building. This is global radiation result on this building. We also in parallel detect windows, not perfectly, because you can see that there are some blinds that prevents to automatically detect using this machine learning techniques. So we should have to improve this. This is one of the perspectives. So for this demonstration, manually, we should have correct manually. So it writes that all the opaque elements on the blind wall and here. So the idea is to select the appropriate building surface for solar panel installation. So the roof and the red part of the facade, and also considering a minimum amount of irradiation for facade. So that's why we can here identify the potential productive area and roof southwest facade, west this one is east facade, not at the opposite, so the contrary, sorry. Then is the global results. So it is economic and technical analysis. We compare without facade, so just roof and roof plus facade, with some key performance indicator like the production, the total power installed, self-sufficiency, cost, profitability, like payback, etc. So many indicators. So you can see also the benefits of using facades. We improve the self-sufficiency. The payback is not so bad, even using facades. We increase the production of 25%. There is globally, with roof and facade, good coverage of energy demands during the winter period, which is the most critical period, as you can guess. Here, there's the monthly balance between the demands, the self-consumed energy, and the risk sold back to the grids. Just here we can have a finer analysis at early scale. We compared the global energy and facade on roof, and you can see that during the winter from October to March, we have more irradiation on the facade than on the roof. But of course, in terms of electricity production, this superiority is a bit reduced because the efficiency of panels facade is less than on roof. But even that, from November to March, we still produce more electricity. And another thing is to see what is the share, what is the contribution of reflection. So in blue, this is the primary radiance, diffuse plus direct. And here, the reflection. So this is the vertical profile, the roof onto the ground. And you can see that proportionally, the reflected part increase because it has some reflection from the ground. So we can see that the reflection part on facade is important, between 20 to 40%. My last slides, it is about monitoring system that we have installed in Geneva. So we have installed two facades that are face-to-face with pyranometer to measure the radiation. On each floor, there is also an autonomous solar power supply with battery to supply pyranometer, data logging, and like that we don't disturb people, residents. The idea is to have this monitoring to compare and validate our models. So the perspective is to use that to validate model. We're also preparing to process solar catastar on the facade in Geneva, and also migrating the code, MATLAB code, to a C++ environment that will enable us to speed the computation. Thank you for your attention.
Thank you, Gilles. It's very interesting. We move further to the last presentation for this session. Then we have the question and answer session. So Reidar Stålen is the next speaker. Yep. Okay, so Reidar is currently working on a PhD on applied fire safety of PV installation on buildings at Norwegian University of Science and Technology. His supervisor is here as well, right? Anne Stein. Very nice to see you as well here. Thanks for coming. The focus of his work is to understand and mitigate the consequences of case of fire in a building with the PV installation. Reidar has been working at RISE Fire research for the last 15 years. Reidar, floor is yours.
Yep. Can you use this one? Yes. Yeah. Let's see. Where is this? Does this work now? Yeah. Sounds nice. Okay, interesting to speak to this crowd here, which is very into photovoltaics, but maybe not that much into fire. And for me to get a different perspective on also other aspects of photovoltaics that is important, and not just the fire things that we are most interested in. So I'm going to briefly go through some aspects related to fires and PV installations, what can cause fires in PV installation, some data on fire probabilities, and also a brief overview of fire testing and fire documentation of PV modules, and to show an example of a large-scale test that we did on a BIPV facade a couple of years ago. Well, so PV installation is an electric installation, and like all other electric installations, they can represent a hazard of ignition by electric faults. Not to go too much into details here, but as the electric installation is continuously operating over longer time, it is a type of installation that might be more susceptible to causing these type of errors, as they will be continuously working under high load as long as the sunlight is making the installation produce electricity continuously over several hours. So it's very important that all the electric connections are good, and that they continue to be good over the entire lifetime of the installation. So if there is a problem, it can cause heating and electric arcs that can cause fires. And also, fires can also be started anywhere else in the building and spread to the facade or to the part of the building with a PV installation. So it doesn't necessarily have to have anything with the PV installation as an ignition source to do. And a little bit about fire probability. Difficult to get good results from poor statistics, and also very the spread of different statistics from different countries give completely different fire probabilities. So this one paper here has made an attempt to overcome these barriers and to make some global estimate of how many fires can we expect from PV installations. And this number, 29 fires per gigawatt installed, is maybe the best estimate that we have so far. And in a Norwegian perspective, with our what is it 300 megawatts total installed, there would be 9 fires every year, so not really a big issue so far. But of course, increasing the amount of PV installations will also probably increase the number of PV related fires. Also, this the second reference that I've found is also based on very old data. It's published 10 years ago, referring to that building integrated PV installations are more have approximately 20 times higher fire risk than building attached PV modules. Very disclaimer on old and maybe not representative data, as these installations were, but the publication is from 2013, and it looked at the installations in Germany from the years before that. So a lot has happened in the building integrated photovoltaics since that. So hoping to be able to find better and more relevant data for modern BIPV systems. And a little bit on the different lot of figures and standards and numbers here, so don't worry too much about that. But in maybe one of the most common standards to test PV modules against is the IEA 61730, and that contains a lot of different tests that the modules need to withstand. And there is one of these tests is the ignition test. It's basically a small match-sized flame that should be held against the PV module for 15 seconds, and it should not catch fire from that. So that's a very small scale test, and does not necessarily say everything about the relevant fire properties of the products. Also, other test UL 1703 is a larger scale test, but as far as I've understood, only relevant for roofs. And also, you have the Euro classes that can be used, but not that commonly referenced in BIPV products, as far as the study here has seen. And also, there are several countries that mention different types of large-scale facade tests that is required for facades with combustible materials on them. And as most of these BIPV products will be classified as combustible because they contain some plastics and some other combustible materials, then these types of large-scale testing standards may be relevant for these systems. It has, however, been very difficult to find data on, at least available in the public domain, on products that has been tested and certified, documented against these large-scale facade tests. But there probably are some. But we did one ourselves 2 years ago. This is called a facade test called SP Fire 105, which is basically a facade. This is, 4 by 6 meters. And it simulates an apartment here with a fire flash over, and where the flames extend out from this opening and expose the facade to a relatively severe heat load. And compared to the matchstick 20 millimeter large flame, it's completely different scale. So this was a BIPV system that we tested against this standard. And let's see now the fire started, and this room is going into flashover, and these flames are exposing at least the lower 2 rows of PV modules, and the black smokes covers everything else, so you can't really see much what is going on. But afterwards, when this fire was finished, you could see that the 2 lower rows of modules was completely damaged, and the aluminium fixing system was melted, and the glass had broken and fallen down. And also we saw fire propagation upwards in the cavity between the building surface and the PV modules. Basically, the fire propagated in the polymer backsheets of the modules and propagated upwards, causing also several other modules to fall down on one side of the facade. And on the other side of the facade, the fire was not propagating above this level here. So yeah, that basically shows something that can happen in a fire in a facade with PV modules. This is just one test of one type of system, so it's not something that we would say that is relevant or representative for all other modules. But and we're very interested to see other systems that have been tested in similar scales, to see what other types of failure mechanisms that we can expect and should prepare for. Yeah, that was a brief introduction.
Okay, if someone can help with the chairs, we need 3 chairs here. Before the Q&A session, I just want to mention that another PhD working with Anne, Cristina Sanfenio Meglia, she was here before. I don't know if she's still here, has done a poster, and they are both in Frick, Fire Research of Innovation Center. So if you have any questions, so Anne is here, so she probably will be very happy to answer questions. Okay, we move to the question and answer session. There is any question from the audience? And then
Hi, great presentation, everyone. I'm wondering, my question is to Hassan and also to yourself on fire. Building integrated photovoltaic thermal systems, which have, because this is a pretty novel technology, combining the airflow behind the photovoltaics to cool the photovoltaics. How much has that been implemented here in Norway? Do you see scope of that? Because that can be used to heat up the air, preheat the air if it's going into a heat pump. So are there examples of projects like that? And second question, similarly from a fire perspective, do you see maybe that could, again, it's out of curiosity, do you see that maybe that could exacerbate a fire situation because you have air going through a channel behind the photovoltaic? So just try. Yeah.
Yeah, I can maybe comment on this this air cavity.
Yes.
Basically the flow of air behind this cabin that is in PV modules. Okay, green. That's better. And that's not something particular for PV modules. We have that in other types of wooden claddings and all, basically any other ventilated cladding system, and that this air cavity is one of the challenging areas of preventing fire propagation in facades. So, but I'm not very familiar with these. Yeah. Yeah, I have no experience with that and don't know if it's common in Norway. I don't know if you.
I don't think I haven't actually done any BIPV project in Norway. What is two main ways I can say? The first one is that the main application of BIPVT is to help ventilating the PV system to just decrease the degradation rate, to expand the lifetime of the BIPV system. But here in Norway, we don't need that much because it's cold climate. So exactly that's one of the main advantages in Norway. Normally you have longer lifetime BIPV system here in Norway compared to other parts of Europe, and also lower degradation rate. And also the other thing that the BIPV system, BIPVT system, increase the complexity of the entire BIPV process. Kind of already complex, something. By adding thermal and BIPVT, it just make it. I know that it's really efficient, and also, I mean, for the BIPV, you have the efficiency of 20, but if you make it BIPVT, you can reach the efficiency of 80% or something like that. But yeah, it just make this project more complicated, and I think we need to reach a kind of make a level, really good level of the rolling out for the BIPV, and then just add a bit more complexity on that. Maybe in Norway at least, might be different situation in other countries.
Makes sense. Thank you.
Okay, another question, right?
Yeah. It's a question to the Hassan and then to Reidar. Hassan, I tried to figure a number of the cost per kilowatt hour for that marginal cost for BIPV. Have you done such research what the cost might be?
That's the BIPV.
Because the BIPV has an extra cost compared to another facade.
Yeah.
So what does that mean for the customer in cost per kilowatt hour? Have you done such research?
Yes, but the thing is that, I mean, when you have this PV project, not on building, so you normally can easily say an average, because normally for so you have fixed angle, everything. When you talk about the average for PV system, not in building, not in urban area, so you almost know that, yeah, how is the. When you say the average, you know what is average, but when it comes
Not
to
an average,
BIPV.
Have you done such research about
Yeah, but
prices?
it's really exactly here, I think just about the levelized cost of electricity, LCOE.
Yeah.
Or BIPV on building scheme in average in Norway as well, so. It just showed a slide for two scenario, yeah.
Yeah, so scenario 2 was good.
Yeah.
Scenario 1 not so good.
Yeah, but the one was because of the considered all the investment, including the role, the BIPV role as a building envelope material and also as a power plant. But scenario 2 was just this added cost or marginal cost for the BIPV system. Yeah. And there we saw that for Europe in average, it was the levelized cost of electricity, if I remember correctly, was less than 10 euros per kilowatt hour or something like that.
I will check that for later. So the interesting point.
Yeah.
Reidar, I'm worried about fire. So when I saw the test you did, I heard about the test. I asked my colleagues that are experts in making panels, and they first asked me what kind of panels do they use, because they don't think the foil we are using or the backsheet we are using can cause that much fire. Do you have any reference to the panel you use, so we can also check how good our panels are compared to that one?
Yeah, I don't have. I will test these panels further in the cold color image, etc. But based from what I saw, it's relative. It's basically just a thin polymer film. It does not contain a lot of combustible material. It's just maybe 1 millimeter or something like that. So it's not really a large heat load, but it is when this combustible material burns in this small cavity, it generates enough heat to maintain a high temperature in that small cavity, and that makes the fire propagate.
This was that one for glass, normally you don't expect something like that. This was from glass.
Yeah, this is the polymer backsheet. So at least if the glass backsheets, and although if the outer skin of the building is also not combustible, this type is done with the gypsum board. So, yeah, so it takes just a little small amount of combustible material in that cavity to make a fire propagate. But of course, if you can keep it at zero, then yeah, you wouldn't have that problem.
Just for glass BIPV, normally we have really high fire safety for the BIPV system. I know that, but for glass backsheets, not that much.
Okay. Thanks a lot. You can discuss this later on. Yeah. But do you have any other questions for the presenters of session? Or was 4 now 3? Any question for Jill? Okay, if not, I will have a question for you, Jill. You are developing a lot of this simulation analysis and engine now for the velocity and so on. How much is the improvement in terms of accuracy with these new methods that you are developing, and how is the practical use with, like, let's say, broader public, not municipality, but are the common people really using this tool, or how do you reach them? That's not for the technical part, of course, but for the solar cadasters that you are developing. Which how is your experiences in working with both municipality, which is more public authorities, but also common people?
Yes, but your first question, yes, I did mention that, of course, this radiosity approach to process reflected radiation, and we also compare the simplified approach with the traditional approach on, let's say, typical urban canyon. The results were very close, so very satisfying about validating this approach that enabled to really speed up computation time. So this is probably the first question.
And how much have you experienced with the improvement of accuracy, let's say?
Accuracy not, because the idea we were not so accurate, but we are very close to be so accurate as we would have used the traditional approach, but which is not feasible for large urban scale. So the idea is to get close to a more accurate approach, but which is not possible at a large scale. So yes, reading the paper I mentioned, there's all the information about the accuracy, how we were accurate. And about the second question, so I can just answer according to the solar catastrope of the roof that we did for the Greater Geneva. So this is a new interface for the public. So we don't, so far we haven't had a lot of feedback, but some feedback anyway, which is very difficult. We go very far in depth about that, because we discuss not only if it is a good roof or not, but we also propose some technical, economic, technical indicators. So we can also simulate or make some simulation. So maybe for some public a bit too complicated. So we address a very wide range of public, professional as well as normal public. So but the first feedbacks are very good. So there's a big challenging addressing a wide range of improvement, of course.
Thanks a lot, Jill, and thanks a lot to Radar and Assam. So we can move to the last session. Okay, last session is on competing views of urban services. The first speakers is Erlend Andenas. So just give me 1 second, I think. Presentation here.
There you have it.
Yes, but I would like to introduce you before you start. So Erlend is working as a postdoc in the research project of SFI Klimaskyddfanten, risk reduction through climate adaptation of building and infrastructure. His PhD project concerned risk assessment of blue-green roof and was completed in 2021. And Erlend's background is building physics and building technology. This is what you were looking at. Please, Erlend, the floor is yours.
So I haven't worked with solar panels since my master thesis days, but I'm mostly on roofs, so dabble a bit in it. So for a roof in an urban setting, there's many difficult choices to be made. This is an example of downtown Oslo. It's a very dense urban area with surface covering that's mostly impervious. Rainwater will have to flow on the surface instead of infiltrating into the ground. So roughly 50% of all rain that falls there will flow on the surface. There's little green space, little recreational space for people. Few places to hang out, to have lunch, and so on. The electricity cost is high, and there's low capacity in the local drainage system because of climate change, raining more than it used to. And of course, you can use roof to solve these problems to some degree, but not necessarily all at the same time. So you have to choose what concept do you pick for your roof. To start with, we can look at a conventional flat roof, which is sort of the default option for a building. It's what the contractor will build if you ask for nothing else. This is where the roof is used solely as a building envelope. Usually the roofing layer is the top layer. It can have insulation above there as well, but that's not a special thing. There's limited access. There's some for the maintenance of technical systems, so maybe advertising boards or ventilation systems and so on. And you don't get much utility out of the roof. You have here lots of square meters of good real estate that is not put to any use. And that's what you want to change, maybe. But then there's a problem of urban flooding, which is kind of the big thing in the urban planning nowadays, where the drainage system in most cities in Norway is quite old, and it was designed for a rain load that happened before climate change. It's raining 15% more in Norway now than it did 100 years ago, and it will continue to rise by another 15% by the end of the century. And most of it will, or much of it will come in like intense rainfall events. And this requires some adaptation, because if the drainage pipes go full, then it will start flowing on the surface, and if it starts flowing on the surface, it will flow into people's basements and so on. So there are quite strict regulations about what to do here. Here's Norwegian 3-part strategy for stormwater management, where you're required to intercept and infiltrate stormwater for small events. There's a limit to how much water your your plot or size of land can put into the stormwater drainage system. So for medium events, you need some sort of local storage of water, either on the ground or on the roof. For very large events, flood pathway must be established. It's mostly step 1 and 2 that's required. That's necessary for roofs. That's relevant. So if you build a conventional roof on your limited plot of land, you still will have to think about, for instance, stormwater management. So if you don't utilize the roof, you might have to lose the ground space. Have to set aside space in the ground for a pond or something to manage stormwater. So green roofs are built to, or blue-green roofs are built to address that problem, where you have living plants on the roof and use them as a sort of sponge to soak up rainwater. Guy was talking a bit about that earlier. I mean, and green roofs again, usually no public access. There's a meadow up here that is mostly access for maintenance. And there is some other factors at work here. You need a bit of maintenance up here, nothing compared to usual lawn, but a couple of visits per year. Weight can be a problem here. If you have a retrofit building, you usually don't have much structural capacity to play with. So you can be limited in what you can put on the roof, for instance. The rule of thumb for green roofs is that for every centimeter of thickness, there's 10 kilograms per square meter of weight. Then you have the common option of solar energy production through solar modules. Everyone else has talked at length about this today, but just listed some of the properties of solar electric roof. Fastening points can be a concern for leaks. That's my topic as well. And it gets worse when I try to combine it with other things. And it's also possible to put entire parks on the roof if green space and recreational space is what you need, with lawns and trees and bushes and even playgrounds or cafeterias or park benches to create a public space or a terrace on the roof. And then you need sort of measures for public access and safety, for instance, fire escape routes, railings, and putting technical equipment so that the public can't tamper with it. If you put a solar panel in the middle of a park, and on day 1, someone will try to pull out the plug to see what happens. And this is quite maintenance and cost intensive and very heavy option. So it's, yeah, and it weighs a lot, so it's not usually suitable for retrofit projects. So what to choose for your roof? That's a big question. Because there are parameters to consider, like the upfront investment costs, maybe the lifetime costs. This roof is going to pay itself back over time, for instance. You heard about that. But also, this roof can save you money because you don't have to use a pond or an underground water retention basin. And the park, I mean, if you charge for access or have a lucrative restaurant up here, you can make money on that as well. The CO2 emissions, similar story. You're paying back your CO2 costs with exporting electricity. But that means that you also might have to have a concrete tank somewhere to store the rainwater. And of course, the risk of building defects should always also be considered. It goes into the lifetime costs. What happens if you need to repair here? You have to organize quite a lot, take away the plants, repair the whole, put the plants back, and so on. So there's each solution has benefits and drawbacks. So to make that choice, it's very important to identify the needs and possibilities of the roof in question. Sometimes it's easy. For this roof, you would put solar panels on it if you value your money. You don't need a rooftop park if your neighbor is Versailles. And of course, if your building is in the middle of the ocean, you don't need stormwater management. So sometimes it's easy. But other times you got a tiny dingy roof in the middle of the city and you need both green space and electricity and you need stormwater management and you have next to no space to work with. Because those priorities, none of them go away. You must address those needs somehow anyway. And if you commit the roof to solving one of them, are you then solving the other ones effectively or efficiently? Would the other methods maybe cost more or less? For instance, if you put PV panels here or you put a green roof here, how much will it pay for electricity? How much will it pay for eventual stormwater management? How much more could you charge the tenants here if you had a rooftop park they could access? They could maybe pay a lot more rent if they had a park to themselves. That's some of the questions. So making that clear understanding of needs, opportunities, and goals, that's essential to create a good roof. And of course, you can combine uses as well. Put aside a little space for a small park and a small solar production facility and a small green roof and so on. But then you're making compromises because there's limited area on the roof and there's limited sunlight. And the complexity goes very high up. I mean, try to imagine how many different disciplines of workers and planners and consultants you would have involved on this roof in this project. There's electricians and there's gardeners and there's playground safety and there's the restaurant owners and so on and so on. And that will end up in building defects somewhere. And at the same time, you get very little electricity, you get very little stormwater management capacity, and you get a very small park. So you might end up with not quite enough of anything and still have to address all your needs in a different way. Although some utilities can be combined, solar panels on green roofs, if the roof can carry the weight of it, is usually considered a good idea because the green roof cools down the roof and the solar panel works best when it's not overheated. Of course, you need the gardener and the electrician to work together in some fashion, and the weight can be a concern. And of course, the plants also need photons to live. You can't just carpet the whole roof with solar panels and expect plants to live underneath. So you might have to have somewhat fewer solar cells. That's a compromise. So in general, we can say that the utility of whatever you're building on the roof that's shared between the different uses you put on the roof, but the complexity is additive, sorry. So just to use to put some conclusions, you can use the roof to serve a function that would otherwise be addressed on ground level or through other means, like just paying for the electricity from the grid. You need to conduct this systematic assessment of benefits, opportunities, disadvantages, and even risks. The right answer for the roof, that depends entirely on what's needed and possible. You must weigh the parameters that's relevant for your project. Consider the lifetime of the roof and the cost of all alternatives. It will never be zero. So that's my presentation. Talk for mine.
Thank you, Alan. I hope you will be available later on for the question and answer session. It's now turn of Silvia Croce. She is a postdoc researcher at Institute of Renewable Energy EURAC Research in Italy. Her research work aims at gaining insights into solutions for integrated design of the urban built and natural environment. I hope it opens. With focus on outdoor microclimate, thermal comfort, energy saving, and renewable energy production. Let's see. Okay. Sylvia, the floor is yours.
Thank you. So actually, it's very nice to come right after Erdan's presentation because there are many of the topics I will be speaking about that perfectly links with what he has just presented. I will actually broaden up a bit what was previously discussed, looking at the use of urban surfaces in a bit broader way, mainly for climate resilience objectives, and I will focus on case studies in Italy in particular. Actually, when we are talking about using urban services, we should consider that urban services are not just roof or facades, but we have also ground surfaces. So actually, there's a high exploitation potential. It is estimated that roofs are around 20 to 25% of the total urban surface, and the surface of the facades is almost double. So there's a lot of space that might be wisely used for many different uses. We have heard speak quite a lot about active solar energy today, but actually there are also passive solar energy systems. As we have just heard, green solutions are also an opportunity, but there's also water, which is still also linked to solar when we think about evapotranspiration, for example, for cooling purposes. But there are also the possibility to allocate some surfaces for urban agriculture or to use cool and innovative materials, as we have also heard before in Martina's presentation. And actually consider all these different uses, all these different solutions might contribute to various benefits and purposes at the urban scale, ranging from climate management, but also to food provision, energy production, water management, as we have also already heard, etc. So actually, what's a bit still the barrier and the struggle is that mainly the approach to the design of urban services is biodimensional, and sectorial. So many of the solutions you can see in the different projects are actually focusing on a single objective or a single solution, or just a kind of surfaces. So for example, roofs or facades. What is needed is actually somehow to support urban decision makers, designers, and municipalities in defining the use of urban surfaces, taking into consideration the fact that still is a complex and multidisciplinary approach and problem, and there is the need of both quantitative and qualitative data, because of course we can do wonderful simulation, but then we also need to have a practitioner implementing the project, and we have to make them social acceptable too. So actually there is a broad range of methods which might be used to gain data and to gain qualitative information from on-site monitoring data, results from the environmental tool, using multi-criteria approaches then to evaluate all these data available, but also then engaging stakeholders in the co-design and definition of the project for each case study. What I am presenting today is actually what we at Europe Research are working on in the city of Bolzano. As you can see, it is located in northern Italy. It's in a valley close to the Alps. It's a very nice alpine city, but then you can think, okay, it's in Italy, Southern Europe, but still close to the alpine regions. Yes, but in summer, if you look at the news, usually temperatures in Bolzano are like temperature in Sicily, so in southern Italy. And that's obviously one of the main issues that the city is struggling with. In particular, we are working on Bolzano South. That's the industrial area of the city. is the one you see here in red. And it's actually is more or less 1/3 of the total built-up area of Bolzano. So actually it has a very high influence on Bolzano microclimatic conditions and on the development of the urban Italians effect, as you can see also in the picture in the middle. Actually, we have done a monitoring campaign in 2020. The daily average air temperature was 2.5 to 7 degrees higher in Bolzano Sud than in the surrounding areas. And as we have also heard from Erland's presentation, there's also the problem of permeability and stormwater management. You can also see from the aerial image that actually the area is mostly gray. It's concrete and asphalt, and actually the permeable surfaces are less than 9%, considering also the roofs, because there are some green roofs already presented in the area. So actually, these are the main objectives and the main needs that should be pursued in Bolzano Sud. Obviously, the main two are fighting urban Italian and overheating and increasing the share of permeable surfaces. But there are also the need for vegetation because there are no green area, and for the reduction of pollutants and emissions, because the main connection from the city through to the region are actually crossing Bolzano South. What we are doing in our studies is actually aiming at moving from a single function for each urban surfaces, first to multiple functions. So at least considering solar energy production in connection or with the possibility of having green roofs in the area. To this aim, we had a small project which was called the Entrepreneurial Activation Process that was financed by Bolzano municipality, actually to evaluate and somehow also encourage private stakeholders in the area to integrate green roofs on their building. What was done mainly was first to interview some of the main local stakeholders to understand the potentialities and also the barriers they perceived for the implementation of green roofs. We then had the public presentation of the preliminary results of the interviews to further discuss the topic. And then we hold a final public workshop with also a site visit to an extensive green roof in the area to also involve the citizen and all the stakeholders working in the area. We had many interesting results already, but what was most interesting was actually to understand the perceptions of green roofs from building owners mainly. So they are definitely not people really scientifically knowledgeable about the topic. So the perception was actually that green roofs are very relevant for reducing soil sealing, increasing water retention. They could also contribute to energy efficiency of their building, but they perceived that they could not reduce urban Italian and overheating in the area. They saw them more as an added value for their company, just something also to advertise on their website to look greener, actually. And they were kind of most of them, I would say, are also aware that there is a conflict between active solar systems and greening solution on the buildings, especially on the roofs. So this was also a point of discussion with them, and they mainly said, okay, but we choose just one of the two solutions because otherwise the costs are too high for us and maintenance becomes an issue. So these were the first results we got from the discussion in the area. What we wanted to do next was actually to move from considering just multiple function to considering multifunctionality. So we wanted to analyze the main needs of the area and solve them in a multifunctional way, so integrating several surface uses in the area. How was this done? It was actually done through several methods. We had some on-site monitoring campaigns I want to present today. We did some environmental analysis, both social and solar and microclimate analysis, and then we applied a multi-criteria approach. I will just briefly show you the environmental microclimatic analysis we conducted. So we created some surface use scenario. The first one was considering the application of nature-based solutions and their effect on microclimate in a typical hot summer day. Here you can see what we applied. So we consider intensive grid roofs and the creation of 2 new public green areas in locations which currently are just brownfields. And these are the results in terms of average air temperature reduction at the hottest hour of the day and human thermal comfort. You can see that the higher impacts of human thermal comfort are mainly in the green areas at ground level, but still there is an average reduction of 0.5 degree of the air temperature. We also consider the use of cool materials, so reflective roof paints and white topping on the major roads crossing the district. And you can see that the air temperature reduction was higher, but we have analyzed a worsening actually of human thermal comfort due to the increased reflectant radiation connected to the use of cool materials, so materials with an higher albedo. We also analyzed the impact of solar active systems, which is currently almost negligible both in terms of air temperature and human thermal comfort. And we then analyze all these results applying a multi-criteria approach. I won't go much in detail into this because it was a quite long approach, but where you see the green is actually we have an improvement in terms of the main needs of the area, while the red were actually solution worsening the condition. Through this multi-criteria analysis of the results, we actually selected and prioritized the different potential surface uses to be applied in the area. So nature-based solutions are the one actually contributing the most. Then there are also cool materials and energy systems. So we did a final scenario, actually creating a pattern of all these different uses, integrating green roofs, public green areas, but also the use of reflective materials. We simulate the solar system just as they are today because there were no more available surfaces actually. And this is the results. You can see that there is an improvement both in terms of temperature reduction and human thermal comfort. So actually in a neighborhood it's very relevant to consider how also to integrate a different solution. And the last step, we are actually working on this right now, so I will just present what we are doing, is actually to move to inclusive functionings of surfaces. So not only considering the more technological point of view, but also a social point of view and a point of view on environmental justice. This is being done through the Just Nature project, an EU-funded project focused on the activation of nature-based solutions, which is also focusing a lot on the principles of the right to ecological space and on biodiversity and ecosystems and all the different challenges related to justice. So here you can see we are mainly focusing on environmental aspects and biodiversity, but we have the case studies exactly in Bolzano, in the area I presented before, in which we will have a green roof on an existing municipal building, which already is hosting some solar panel and will host part of the roof becoming extensive green roofs with the solar system, and the part of the roof will become a high biodiversity green roof. So we will be able in the future to see the different effects of this application, and also we will be able through the project by a co-designing process, including workshop with stakeholders, also to involve all the population in the area. So actually our vision is a bit to move from something like this, which is an aerial view of Bolzano South right now, very gray with just some solar system, to something like this. So more greener, but also more livable and more environmental friendly district. Thank you for your attention.
Thanks a lot, Silvia. That's make me to say a couple of words about you. Silvia has done a PhD in Italy, but master's thesis with me at NTNU.
Yes.
And it's really emotional from my perspective to see how far you got now with your postdoc. I'm very proud of you.
Thank you.
So I hope you can keep going with the good work that
Thanks.
you're doing.
Actually, it was very nice to come back here in Trondheim after so many years. And I also saw there was like a small picture from a master thesis in Steven's presentation about Team Solar. So
Yes, it's yours.
very nice to see that too.
Yes, so, but thanks a lot, Silvia.
Thank you.
Really. Okay, we move on to the last presentation. So last presenter is Johannes Brodzowski. Johannes is now a researcher in SINTEF community in Trondheim, and he has a background in building physics and HVAC system. He has done his PhD on urban physics, urban microclimate and its effect on outdoor thermal comfort and building energy use at high latitudes. Thanks for waiting until now to do the presentation and to be very kind to switch for some unexpected reasons. So thanks a lot, Johannes.
I'm glad to be here and be able to present. I hope you still have some mental capacity left after a long day of many presentations, many very good presentations. So I hope I don't bore you too much with mine.
Johannes, take your time and the floor is yours.
Thank you. Thanks also for the nice introduction. Yeah, my presentation today is about the urban microclimate in cold climate cities at higher latitudes like Trondheim. And I can jump over that one. First, about the background and what actually is the urban microclimate. So, as we all know, cities are under enormous pressure. On the one side from global population growth and ongoing urbanization, but also because a large fraction of energy is used and CO2 emissions are happening in the cities. So there's really a need to create resilient, livable and healthy cities for its residents, which is also topic of some UN Sustainable Development Goals. And also in the beginning, just to be on the same page regarding the scales, when we speak of microclimate, we're at the meteorological micro scale, while the urban microclimate is also moving towards the lower end of the meteorological mesoscale. So microclimate is usually on building and neighborhood level. So that's what we looked at mostly in the work that I'm going to present you now. But what makes the urban climate or urban microclimate actually that special? You have to know that the urban ecosystem is extremely complex and is quite different from the natural landscape. This is on the one hand because of the quite reduced urban biosphere. We've seen in Silvia's presentation that usually urban landscapes are quite gray. There's not that much vegetation, meaning there's there's also less evapotranspiration from vegetation. We've also heard this before, the sewage system, the canalization usually drains away surface water from precipitation very, very fast. So there's also not much to evaporate and cool down cities. And of course, most importantly, there's the built environment with all the buildings which are obstacle to wind, to solar radiation. Plus, they're made up from very heavy and dark materials usually, so they're really good in absorbing and storing solar energy. So all that makes the urban ecosystem quite different from a natural landscape, and that's why it's important to consider this in urban planning as well. Additionally, I want to highlight some challenges that appear, especially at high latitudes. And here you can see a world map with cold climate zones highlighted. And high latitudes are usually the areas between 60 and 90 degrees north or south, but yeah, in the south there are not that many larger populations present. So it's mainly on the northern hemisphere. These areas, the high latitudes, are mostly cold climate or polar climate. But one important part is missing when just looking at the climate type, because two cities that might be classified by the same climate type might still have large difference when it comes to solar radiation. For example, in southern Canada, we have a similar climate type when you see this teal color here, like in Tromsø, for example. But the variability of solar radiation is huge, and this is something that we really need to consider in urban planning. So, as I said, especially in dense city environments, low solar angles in the very north, you have very limited solar access on pedestrian level in cities, or also daylight access in apartments, which is a huge problem. Long winters, cold winters, heating dominated. We see it right now when you just look outside. A lot of snow and ice. And although it might be a little bit counterintuitive right now, because we have -10, -15 degrees at the moment, but there's an increasing risk to populations from heat waves, actually. And there has been some studies from the Norwegian Meteorological Institute on that. And as we can see in their statistics, in fact, the occurrences of heat waves, they have been rising quite significantly over the last decades, and in 2018 reached a record value so far. So this is really something that we need to consider, and there have been some studies from Norway and Sweden documenting the negative effect on population's health from exposure to long periods of heat. And just as a fun fact, there's an old and a new definition for Norway, and the old definition was 3 consecutive days with a temperature above 28 degrees. Now it's 5 days with at least 28 degrees. But in Greece, the temperature level is actually 39 degrees, which is very different from the definition in Norway. But actually this doesn't matter, because the population in Norway is not used to that. It's always dependent on what you're used to from when you were little and grew up. So for people in Greece, this threshold of 39 degrees is equally stressful for the health as 28 degrees in Norway. And this effect has been documented in some studies. So, but how can we investigate the urban microclimate? There are different methodologies, and this is quite interesting and is a lot of fun, as I can tell from own experience. You can mount sensors on any kind of vehicle. Everything is possible: drones, these small carts, bikes, cars, planes. You can use a wind tunnel. We heard a little bit about weather balloons in the last couple of weeks that have been shut down. Or as we did in Trondheim during my PhD, we used some mobile weather stations that you could simply assemble and disassemble very quickly, or infrared thermography. And these data captured from these sensors was used in numerical models that I built for the NTNU campus in Trondheim during my PhD. And yeah, basically computational fluid dynamics CFD is using computers to analyze problems that involve fluid flow, and in this case, air. With increasing computational power, these tools have been able to cover more and more physics and also increasingly large areas, which may make them more and more attractive to apply them for urban microclimate or urban climate studies. So now, long introduction, some examples of the work that was done here in Trondheim. Without going into too many details, the first study I'm going to present you is about the impact of neighborhood design and materials actually on the microclimate with regard to outdoor thermal comfort. Some of you might recognize this area of NTNU campus. So we investigated different scenarios. When here it was the goal to increase solar access. In scenario B and C, it was to close these passages between the buildings to reduce the wind speed. And in the fourth scenario, we changed the surface material so they would absorb more solar energy and be warmer, and therefore increase the outdoor thermal comfort. That was at least the idea. And when looking at the results, also due to time, I cannot go into too many details. But let me just say that on a typical October day, it was a very average October day, quite sunny. Actually, increasing solar access was much more effective in increasing outdoor thermal comfort than wind sheltering. And changing the surface materials of the building almost had no effect on outdoor thermal comfort. In another study where we looked at a similar thing, but with regard to building energy demand, we used a more sophisticated simulation tool, where we simulated a much larger area, about 17 square kilometers, with here the campus in the middle and an area of some buildings around the campus. And when we zoom into this area, we can see that the geometrical detail in the center area is very high when you compare it to this aerial photograph here. And even the trees are modeled with a quite realistic shape as well. And not only that, but when we look at how the air passes through the tree crowns, also that was considered that the wind is slowed down, turbulence is added, and the evapotranspiration from the vegetation is also cooling, in fact, down the air. And this is all a function of incoming solar radiation that triggers the photosynthesis of the trees. And so they're not active during the night when there's no sun, and they're more active during the day when there's actually sun, and when they pump water from the ground into the leaves. So that was considered, and what we did was to simulate different scenarios with this computational fluid dynamics model for 3 one-week periods in summer, autumn, and winter, exporting climate files around a building on NTNU campus into a building performance simulation tool, and simulating this building with these different climate files from these scenarios and comparing the energy output. And the cases that we looked at was the case as it is now, when we delete all vegetation, meaning all the trees and all the grass surfaces from the area, from the whole area, from all 17 square kilometers. When we do exactly the opposite, so we delete all the roads and substitute them with grass areas. And also this high performance neighborhood is basically insulating all the buildings in the area with more or less passive house standards to reduce the energy losses during winter from heating, which also has an effect on the microclimate actually. The case building that we looked at was Centralweg N from NTNU campus. And now when we look at the results of the climate conditions around this office building, we can see that the case with no vegetation, so there's just concrete and nothing else around the campus and in the whole domain. The temperatures during this very warm week in summer were very much higher than for all the other scenarios during this week. When we move to autumn, the differences get smaller, and in winter, in December, there's almost no difference anymore. So solar irradiance really makes a huge impact here. And when we look at the energy use, then we can see that if central building 1 would have had a cooling system, which it doesn't have, but if it would have had it, it would have used 26.6% more cooling energy than in the situation right now, just because of the vegetation that is around the building. So as a summary, solar access is the most important climate variable for outdoor thermal comfort and to reduce the building energy demand during the heating season. It's more important than wind. Although, yeah, we're in Trondheim, so there's not that much sun during winter and it's often cloudy. So sometimes wind is the only real option that we have. So it's still important to consider it. Material properties of the urban surface don't have a huge impact during the studied conditions, meaning in autumn. And it's even less in winter when there's snow and ice on the ground, which insulates even more. Urban greening, we've heard it before. It reduces the risk of overheating and also has a good effect on the health, for the health of people, for their mental health, and also helps with stormwater retention. But more studies are necessary because I only simulated a few days of the year, and unfortunately with the methods I used doing annual simulation is impossible. You would need huge computational resources for that. I used a supercomputer for these simulations already, and it took a long time to simulate, I can tell you. So I think we still have to wait until quantum computers are a thing. And unfortunately, it's not very easy to give general advice since all the solutions are usually highly location specific and it always depends on your setting. So it's impossible to give really general advice. But I think that there should be more around the urban microclimate in relevant study syllabi in university, that you at least know a little bit about the theory and the methods that are available to study it. And I also think that municipalities should implement at least some regulations about urban microclimate, and even if it's just pedestrian wind comfort or something, to include in new city developments in urban planning. That was it. Thanks for your attention.
Thanks a lot, Johannes. Please invite you and Sylvia and Erland to have the last session with the question and answer. Okay, any question or comments from the audience? No, it's a bit too late. Yeah, I can maybe pose the questions. So you are, I think, three of us, both of you, all of you, in the very early stage of your career. What do you think that the study that you have done can really make a broader impact to the society? It's a more general question, quite broad, but maybe you have said something already in your last slides, right?
Yeah, it's a very big question, of course. I think since many regulations deal with energy and also just on building level, the space between the buildings is often forgotten, and I think this needs to be much more considered in regulations and also in study syllabi, I think, because of course you sometimes hear of it or think of it, but it's still not really part of education. Yeah, I don't know if there are some courses that you can take about it, but I've never come across those in my.
This is very relevant what you say, because we are always thinking about people that have comfort inside the building, because we are spending most of our time inside the building, but what's happening around and outside, it's a little bit a domain that should be more investigated. That's a good point. Silvia?
Actually, I definitely agree with what Johannes said. In Italy, even more, the topic is completely regretted, I would say, especially also when we have a lot of opportunity of speaking with municipality, and like they are starting to consider now adding some regulation more in relation to the impacts they might have on energy efficiency, less on other benefits that they might set also in the regulation with regard to thermal climate and human comfort. And actually also when in Bolzano we were speaking with both stakeholders and citizens, they are aware about the impact that PV panels might have on energy production, insulation might have on energy efficiency of the buildings. But then they tell you it's very hot in summer and they don't think there might be a solution at least for mitigating that condition. They can tell you, okay, for example, in the industrial area, vegetation is completely lacking, but and they say, okay, it would be nice to have more trees. It would be nice to have more shadows, but still there is not really the conception of mitigating microclimatic conditions in urban areas.
Thinking about it, I think the central theme of my work is more cooperation between disciplines. So that when you have multiple disciplines involved in a project, they need to all sit down and figure out how do they influence the others, and what do the others know that influence their own work, so that not everyone sits with their own perspective and their own ideas and clash with ideas of everyone else. It's about finding a way to include all the different disciplines so that you can account for energy use and acoustics and fire safety and biodiversity and up and away. And maybe also in some cases that you limit the scope of ambition a little bit to make cooperation more manageable instead of trying to make the roof do everything.
Thanks a lot. So if I can summarize, it's more holistic, multidisciplinary approach, and it's more looking to outside and think, yeah, this is the building envelope is more like environmental skin that can protect to the inside if there is something happening outside, but is less investigated the outdoor environment, or let's say domain. Should I mean, I gave opportunity to enough time to give to pose questions from all of you. Barbara, you have a question? Maybe.
I was actually I was astonished. First of all, thank you very much for the nice presentations, all of you. But I was astonished by the results about the impact of materials on the facades, on the microclimate, because sometimes you are going beside a building with a stone facade, and after some hours with solar radiation. You just feel how the wall is warm and so on and so. So I was astonished. Is it because you had high buildings and large distance between buildings? Could you comment about it?
Yeah, good question, good observation. I have a good explanation for that, I think, because the date that I investigated was end of October, so solar angles were already quite low, and it was on the NTNU campus. We have trees that still had leaves, also large buildings. So the radiation was actually not reaching the ground level a lot where people actually move. And I just looked at the temperature out at 1.5 meters height above ground. So I'm sure that 10 meters up, the situation would have been different, but I think it had to do with the time of the year, especially that this had a very little effect, because I was also expecting much more, and I was disappointed when I saw the results. But then, yeah, just going outside, looking around, I figured, yeah, well, the sun doesn't even get to the level where we need it at this point. But this is exactly the stuff that we need to look at and consider when we have these urban developments, that we plan the cities accordingly so that the sun reaches actually the ground level in exactly these times of the year when we actually need it. So yeah, there's still some work to do, things to learn.
Okay, thanks, Johannes. No other questions from the audience? That's online, I think. No one. No. So I think I close the seminar. Thanks to all of you that remains until 15, almost to 3 Friday. So thanks a lot. I really appreciate you came, and I hope you enjoy the seminar, and there was an inspiration for all of you, especially you on this side of the auditorium. I think the future is yours. We are relying on your work and us on your work. You are still young research students, so I hope you can make differences in the next years. So thanks a lot again to all the presenters, and maybe we'll see each other next year with another seminar, or yeah. So thanks, and have a nice weekend, everyone.
Thank you, Gabriele. Really nice seminar.
Thank you.
Great.
Thanks.
It was a lot of fun.
Yes, thanks a lot.